Namaskar and welcome back to the course on statistical mechanics of phases and phase transitions. We have started the discussion of approximate methods, and let's quickly recap what we did in the last lecture. So, very often in the class of problems we want to study, we will encounter regimes of coupling constants which are not in the perturbative regime where interesting physics occurs. For example, if you take the two-dimensional Ising model, the transition temperature as a fraction of the coupling constant J, exchange constant, is something like 2. So, it is 2 times or 2.3 times the exchange constant. So, this is not in the perturbative regime. So, we want to develop ways to approximate our problem in such a way that we can calculate, we can find the non-perturbative effects even if we miss some other kind of physics. So, we looked at the Feynman variational principle in the last lecture, and broadly the Feynman variational principle, the idea is that we will find a proxy Hamiltonian which depends on some parameter, and then we will find a bound for the true free energy of our system, and then we will optimize on those parameters to find the minimum value of the bound. Okay. So, in this lecture we will look at the Feynman variational principle and apply it to the d-dimensional cubic lattice Ising model. Okay. So, very quickly let us revise the Feynman variational principle. So, our goal is to compute the free energy of the system with a configuration space, the set of all configurations described by the set of all C, and the Hamiltonian H, which is in equilibrium at temperature T, which is same as 1 over beta. So, the partition function is pretty standard, and this is the Gibbs probability distribution, and this is the free energy, and this is the expectation value of any observable quantity that you want to model. So, the Feynman variational principle idea is that on the same configuration space, okay, this will be a script C, you define another Hamiltonian which we call H lambda with some parameters lambda. We do not know the parameters yet, or we do not know which parameters we should use yet, but we know, let us say we know the form of this Hamiltonian and it depends on some set of parameters. So, then from here we will compute the partition function associated with this H lambda. We will have a Gibbs probability distribution associated with this, the lambda system, and there is a free energy associated with that, and you can compute any observable using this ensemble as well. So, the Feynman variational principle says that, this is what we showed in the last lecture, that the true free energy of our system is bounded by some upper bound given by this lambda system. And what is that? That is a sum of the free energy of the lambda system, which is just this, plus the average value of the difference of the Hamiltonians. H is the Hamiltonian of our system, and H lambda is this trial Hamiltonian or some proxy Hamiltonian, and you evaluate this difference in the ensemble defined by H lambda. So, this gives you an upper bound for my true free energy, and to find the tightest upper bound, so what I need to do is I need to find those parameters lambda which leave this quantity invariant, right. So, this dfu lambda by d lambda evaluated at lambda m, which are the optimal values of lambda m, they should vanish. So, this is the Feynman variational principle. So, the most important thing that you must observe is that when you solve this set of equations for finding lambda m, you will see that the parameters of our original Hamiltonian, the coupling constants of our original Hamiltonian are present in this. So, the values of lambda at which this trial free energy is minimized will depend on the coupling constants in H. So if you give me a set of coupling constants of H, I will solve this set of equations non-perturbatively by not assuming that any parameter in the given Hamiltonian are small. I will be able to find a set of lambda m's, and once I get lambda m's, I will use the Hamiltonian associated with that lambda m as the proxy Hamiltonian of my system, and from there I can compute free energy, I can compute any observable and so on. So this is the strategy of the Feynman variational principle. So this is what we had seen in the last lecture, and you will realize immediately that the question is, how do you choose this variational Hamiltonian or this proxy Hamiltonian H lambda? So let's first discuss this in general. So it's just common sense to say that your approximation will be only as good as what H lambda you choose. That's just an obvious statement. So the quality of your approximation will depend on the choice of H lambda. So in all cases that at least that I am aware of, H lambda is made with some physical understanding of the problem, right? In particular, you have to keep the following things in mind. If you are expecting that there is some regime of parameters in your original problem where you are going to break some symmetry, then you must construct H lambda which will allow for such a symmetry breaking. If you don't allow for such a symmetry breaking, then of course you are not going to capture that broken symmetry phase. So at least if you are looking for phases, if you want to get a rough phase diagram of some model, and you believe from physical considerations by looking at the physics of the problem that you expect some symmetry to be broken in certain parameter regime, then you must design your Hamiltonian H lambda in such a way that such a broken symmetry can be realized by H lambda. So this is critical. Okay, now the second statement that I am going to make is a more practical statement. So the practical point is, the problem defined by H lambda must be tractable. You must be able to solve that problem exactly with some minimal resources. That problem should not be as difficult as the original problem. So you should not cook up some really fancy H lambda which you are not going to make any headway with. That will not be useful. So H lambda must be some kind of simple Hamiltonian for which you know some exact solution, or you know some way of computing with that non-perturbatively or whatnot, or something that you can reliably do numerics on without too much difficulty and so on. So in other words, the evaluation of F lambda and H minus H lambda on the lambda ensemble, remember you have to evaluate this probably for many lambdas because you want to find a minimum and so on. So this must be easy. It should not be as complicated as your original problem. You must be able to do this with less resources and difficulty. So these are the two sort of ideas. So one is you should choose your H lambda such that it can capture the physics you are looking for, that you expect to realize. And second is this H lambda that you are going to define must be like a solvable problem. You should be able to solve it reasonably. So as you can see, again just common sense, if you put these constraints, you will find that there may not be a single H lambda. There could be different kinds of H, different forms of Hamiltonian, etc. We could do the job for you. The point I would like to emphasize here is that the choice of what we are going to do is very problem specific. So I would not try to explain to you apart from these general guidelines. There may not be like a very concrete methods to find H lambda. You have to look at a specific problem. So what we will do is, we will focus on the d-dimensional cubic lattice Ising model. So if I put d equal to 1, that's our old 1D chain for which we know everything, or we know the full exact solution. if you go 2D, we know quite a bit, and in 3D we don't know what is the answer, and we can, you see the power of the Feynman variation principle, we will be able to solve the problem in any dimension, at least within a certain h lambda that we will choose. Okay, so this is what we are going to do. All right. So how do I apply the Feynman variational principle to the d-dimensional cubic lattice Ising model? So let's get the basics laid out here. So the Ising model is defined on a d-dimensional cubic lattice with n sides, and this n is L tilde to the d, which we have used this notation quite a few times in the course before, and the sides will be labeled by I. Okay. So the configuration space is of course the set of all spin configurations. So this is a particular configuration C, and associated with this you just take the nearest neighbors, find the spin configurations, multiply them, and then multiply it by the exchange constant with a negative sign, because we are talking about the ferromagnetic model. So at a temperature T, the dimensionless coupling constant can be thought of as T by J, and we will see how this comes up nicely later. So now back to the question, how do I choose h lambda? So since I am in d dimensions, I know from the Peierls argument, I also know that from the exact solution of the transversal Ising model, etc., that for example in 2 dimensions there must be a low temperature broken symmetry phase. So since it is there in 2 dimensions, and since I can conceivably cook up a Peierls like argument even in 3 dimensions, I have not done that in the course, but one can think of doing that, and it is also intuitively appealing to think that when you go to higher dimensions, if there is a broken symmetry phase in the lower dimension, that will persist. So you want to have an h lambda, or you want to design an h lambda that will allow for such a broken symmetry phase to be realized. Okay, and the second desideratum is that it must be easy to solve, right? Okay, all right. So what we are going to do is we are going to design this h lambda by thinking about the physics of the Ising model in d dimensions. Okay, so what I am going to do is I am going to look at a single spin, right? So this single spin is sort of sitting in an environment surrounded by the other spins. So the other spins are doing their own thermal dance, so they are fluctuating up and down and so on. So you can ask, what is this spin seeing from the other spins? So if you think about this, you will realize that the spin at site I here is seeing some kind of effective magnetic field, right? So just you think of taking Si out here. So that will be the sum over all j's which are the neighbors of I, Sj, multiplied by the exchange constant. That term looks like a magnetic field. So that I am going to call this Bi. Okay, if you say this, well, that is well and good, but it's not very useful directly, because this Bi is a fluctuating quantities. Because these other spins are fluctuating, as you can see, I have drawn some random spin configuration here. As in thermal state, it will be fluctuating. So this is a fluctuating quantity, and therefore it is not clear that this identification is useful. Except that when you think about the broken symmetry state, suppose you think of the ferromagnetic state where everything is pointing up and you are at the ground state of the 2D Ising model or something, then you will realize that indeed you can imagine that this B field has stopped fluctuating, if you wish, and you could think of it like having some kind of average magnetic field. So that is what I am calling this is B. So based on this discussion, what I am going to say my h lambda is I am going to imagine a set of uncoupled spins which are sitting on the sides. There is a spin sitting at every side. I am constructing H lambda, and each of these spins is not talking to any other spin but seeing some magnetic field B. Okay, I don't know what B is. I am just saying that the trial Hamiltonian is a set of uncoupled spins in an external magnetic field B. Okay. So in a sense, the lambda parameter that we used for the general discussion, in this context the lambda parameter is this external field which I am simply positing exists, and I am replacing my full I am using this Hamiltonian with non-interacting spins. Non-interacting spins meaning there is no exchange interaction between spins, there is just spins sitting, uncoupled independent spins sitting at each site, and all of them are seeing some uniform magnetic field B. Now friends, I warn you that you should not confuse this with the symmetry breaking field. The symmetry breaking field is added to the original Hamiltonian such as this. This is the Feynman variational Hamiltonian. We are saying that at least in the broken symmetry phase, it is as if each spin is independent and seeing some average field coming from the neighboring spins. So we just model this as a problem of a set of independent spins sitting on lattice sides which are all seeing the same uniform external field. Now why did I choose the field to be uniform? We chose the field to be uniform because we do not want to break translational symmetry. I want to hold on to translational symmetry, but I am allowing for the breaking of the Z2 symmetry. So for example, if I write a Hamiltonian like this, you see that it is not Z2 invariant. So I am constructing a Hamiltonian which is explicitly breaking the Z2 symmetry, but I do not know what this B is. This B will be determined by optimization of the upper bound of the free energy. Okay, so this is the idea. Now you will realize after some little bit of thought that this is a problem that you can solve. If you give me a set of independent spins sitting in a magnetic field, you will be able to solve that problem. Okay. So let us see how to now make headway and how to try to get some solution of this problem. So we would like to find what is the optimum HB, what should be the value of B which will optimize the free energy. Okay. Okay. So this variational Hamiltonian is a set of n uncoupled spins in a magnetic field B, and this HB is given by this expression, and B is the parameter, and remember B, the way we are defining this, has dimensions of energy. So we have chosen units in such a way that all terms in our Hamiltonian will have with the parameters that we are discussing have units of energy. And just to remind you, this plays the role of lambda of our general discussion. Okay, so what I have to do is I have to find the bounding free energy. The bounding free energy Fu of B is F of B, so it is the free energy associated with this system, plus expectation value of H minus HB on B. So remember, the B system has uncoupled spins. Okay. So I want to find this expression. Okay. For this, all I need is the solution of the problem of a single classical spin with values plus and minus 1 in an external magnetic field. So this is why it's called H1. That means that it's a Hamiltonian of a single spin in a magnetic field. This is all we need. So the answer for this is very simple. You can just do it in your mind. So the partition function is just 2 cos beta B, right? The free energy is just the minus T times this log of this quantity. The magnetization, which is the average value of this quantity S, or the expectation value of that quantity S, that is tan h beta b. This is also very easy to compute. Now, here is a very nice result. The fluctuation in the magnetization square of that turns out to be 1 minus m square. I invite you to prove this. It's a very straightforward thing, but it's this is something worth knowing. Okay. So, please pause the video and verify these results. It's pretty straightforward. Okay, we'll proceed now on to the computation of the free energies. Okay, so this Fu has two terms. The two terms are the Fb and H minus Hp. Now these are uncoupled spins. There are n of them. Remember, we have n lattice with periodic boundary conditions. So Fb is n times the free energy of individual spins. So that's just very straightforward. Okay. Now what we would like to do is we would like to evaluate this quantity, the expectation value of H minus Hb, in the B ensemble, in the ensemble where I have these uncoupled spins sitting in a uniform magnetic field B. Okay, so I will walk you through this slowly. So I have to compute the expectation value of this in the B ensemble and the expectation value of Hb in the B ensemble. So first is these in the B ensemble, the spin at I and j are completely uncoupled. So the expectation value of Si, Sj in this B ensemble is the expectation value of Si in the B ensemble multiplied by the expectation value of Sj in the B ensemble. They are independent variables. And here I just do the algebra and just get a plus sign here. Okay. But we just computed in the last transparency that the expectation value of the spin is just tangent of B, and we haven't broken any translational symmetry. So this quantity will be the same at all sides. So I'll just get a square of this for every link in the system, right? So this is summing over all the links of the system. Now, if you are in d-dimensional cubic lattice, you can easily see that there are d times n links, and that is where this factor of d times n comes up. So this term, the Ising term, gives a total contribution to the left hand side here, which is minus d times n times j, the exchange constants, times tan h beta b whole square. And this one is just n times b times the expectation value of this n, because there are n spins, and that's what you get. Okay, so now if I add up these things together, I will get the total Fu, and mind you, always check whether it is correctly extensive. So you will see that it's proportional to the number of sides, which is very nice. Okay. Since it's proportional to number of sides, I can find a free energy density by simply dividing it by the number of sides, and this is what I call little FUB. So it is a bound on the free energy density which depends on B. So now we can ask the important question, what B should I choose to model my system if my J and T are given? J is the exchange coupling of the original Ising model in d dimensions that we want to model, and we want to study, and T is the temperature. So what do I have to do? I have to minimize this quantity with respect to B. Okay. So we have to find the optimum HB. So when I do this algebra, it's a very straightforward thing. You can do it very easily. You will see that setting the derivative of little fu with respect to B equal to 0 will force an equation on you which says that the optimal value of B will satisfy this equation. So it says that B divided by 2dj is equal to tan h B by T. Okay, just whenever you do these calculations, make sure that everything is dimensionally okay. So remember, B had dimensions of energy, J has dimensions of energy, so the left hand side is dimensionless, and you can only take tan h of a dimensionless number, and here B has units of energy and T has units of energy, and so this is also dimensionless. So everything is nice and good. So now you see, I've reduced the problem of finding this to some simple mathematics. Okay, So let me walk you through the solutions. So you will see that the solutions of the optimal value, which is Bm, will depend on the coupling constant T by J. Okay, and if you stare at this, you will realize that the natural coupling constant to use here is T by 2dj, because you see I can write B by 2dj, so this will become a dimensionless number, and since I divided by 2dj, I have to multiply that by 2dj, and this will be T by 2dj in the denominator, and that is the dimensionless temperature. Okay, so now what you will see is that I have to plot two curves. So this is, this is the curve, B is equal to this B by 2dj, that's that blue line, that is the left hand side, and tangent is the orange curve. So whenever T by 2dj is greater than 1, so for example here it is 3 by 2, you will see that there is only a single intersection for these two curves, and that is at B equal to 0. And therefore Bm, when T is greater than 2dj, is 0. So effectively our trial Hamiltonian is 0. So there is nothing interesting going on at high temperatures within our trial Hamiltonian. So at high temperatures, the proxy system we have is a set of uncoupled spins with nothing. They don't even see any magnetic field. They are just randomly fluctuating. At T equal to Tc, at T equal to 2dj, you see that these lines become tangent to each other at the point B equal to 0. These curves become tangent to each other. And when temperature is reduced, so this is T less than 2dj, you will see that this equation will produce three solutions for you. There is a solution with a plus value, which is somewhere here, and a solution with a negative value, which is on the left side here. The magnitudes of these two quantities will be the same. And if you analyze the set of equations that you have and all the related information that's available to you, you will find that these two are minima of Fu, and this point at B equal to 0 is a maximum, local maximum if you wish. Okay. So when T is greater than 2dj, summary of what I just discussed, Bm is equal to 0. When T is less than 2dj, there are two solutions with magnitude not equal to 0, one with plus value and the other with minus value, and Bm is 0, corresponds to a higher energy solution. So we don't even worry about this when T is less than 2dj. Okay, so this is looking very interesting. So what is the physics of this solution? So the first thing is that we can compute Bm by solving those equations numerically. So the solution is B is equal to tan H B by T. That solution can be solved numerically, and we are making no assumption about how big T or how big or small T is compared to J. So you can pull off this solution on the computer and you see that up until, if you start from high temperature, T is greater than 2dj, this B is equal to 0, Bm is 0, and when it's less than that, you can pick up this solution, or mind you, you can pick up the negative solution, right? So what it is telling you is that there is a Tc in the system. Why is there a Tc in the system? Because if B is equal to 0, then my trial Hamiltonian HB with B equal to 0 has Z2 symmetry, because Hamiltonian itself is 0, right? But when I am below Tc, that system has now a magnetic field effectively. So Bm is non-zero. It can be either positive or negative, right? And it breaks symmetry whether you choose it to be positive or negative. And the fact that the positive Bm corresponds to negative positive magnetization and negative Bm corresponds to negative magnetization tells you that the symmetry can be spontaneously broken either on the plus side or minus side. Okay, but mind you that you have also got an expression for the Tc. It also tells you that the Tc of the system is 2 times d times j. It found an expression for the transition temperature as well. Okay, and remember, this is not a perturbative result, right? The value at which Tc is occurring is not a small parameter in anything. And now, since you know that I have this, my Hamiltonian acts like a proxy for the real system, this HB Hamiltonian, I can put the HB Hamiltonian and find the order parameter, which is the magnetization of the system. And you can just convince yourself that this Bm by 2dj will be exactly the magnetization. And therefore, these two plots are actually the same, just labeled differently, right? And you will see that the magnetization is 0 until here, and it takes off below Tc and goes up and becomes 1. But this is exactly what we have seen in the experiments, right? Remember the first couple of lectures of the course, and I have shown you data as like this, and so it looks very much like what we see in experiments. So we have now obtained a phase diagram of the system saying that, okay, the system has no magnetization for T greater than Tc, which is given by this, and there is a magnetization that is developing and it becomes 1 as I go towards T equal to 0, which is exactly what we expect. Or is it? Okay. You can do a little bit more. I have not shown the details of this calculation. They are very straightforward to do, so I encourage you to do this. If you look at the regime close to Tc, which is what I am sort of circling here by this pointer, and you define a little t parameter, which we have done several times in the course now, you can define something called as the distance to the transition, which is a dimensionless number, t minus Tc by Tc. You will be able to show that when t is less than 0, which means you are less than Tc, this magnetization grows as square root of T. Okay, this actually just follows straightforwardly from the analysis. You have to work it out, but it can be easily worked out. So what this is telling us is that the critical exponent of how the order parameter grows as a distance to transition is half. So this is called, the convention for this critical exponent is beta, and it tells you that beta is equal to half. So not only have we solved, we have got a phase diagram, which we are very excited about, we have also got a critical exponent. So you might think that this is an excellent achievement, except if you pause and think about things, you may wonder whether it is worth celebrating. So certainly the phase diagram looks okay from d equal to 2 and d equal to 3 perspective, because we know that d equal to 2 there is some symmetry breaking. But our Feynman variation principle also tells us that there will be a magnetized phase in d equal to 1. Now this is terrible because this does not happen. We know that the exact solution, we have solved the one-dimensional classical Ising model exactly. And we know that there is no magnetized phase at any finite temperature. So there cannot be a phase transition at d equal to, remember, 2dj. So it's saying d equal to 2j. Certainly not. So something goes wrong with this Feynman variational approach in d equal to 1. Terribly wrong. In fact, it doesn't get the qualitative physics right. Okay. In d equal to 2, this Feynman variational principle predicts a Tc of 4j, but we know the exact Tc, we have computed this, and the exact Tc is something like 2.3j, which is significantly different from this. So what you are finding is this model here is partial to ordered phases. That means it wants to prefer ordered phases. You see, because the temperature at which the ordered phase dies and the disordered phase starts, namely the paramagnetic phase, in the exact solution is 2.27 J. So in the variational principle way of doing it, we find that it is 4J, which means that the entropy associated fluctuating things, etc., which destroys order, that is not able to win over in this variational model. So there is something missing in the variational model. Okay, so okay, this is a bit disconcerting, all right. So let's see a little bit more. Now we have got that it predicts a value of beta equal to half in D equal to, which is true. This prediction of beta equal to half is true in all dimensions. It doesn't depend on dimension. The variational result does not depend on dimension. But we know that in D equal to 2, it is not half. It is in fact 1 by 8. Okay. All right. So now this is looking a little bit more worrisome. Okay. We can go further. We can do more analysis, and I invite you to do this. We can take HBM as the proxy Hamiltonian. This is a crude calculation, granted, but it is a useful thing to study. You use this proxy Hamiltonian and you evaluate the susceptibility. Use the Kubo formula, use HB, M, the BM that you have computed, and just evaluate the susceptibility. You will see that the susceptibility does 1 over T at high temperatures. That is where, and that's exactly what we expect. At high temperatures it does 1 over T, and this is exactly 1 over T. And at low temperatures it goes down exponentially. This is also what we found by perturbative calculations of the, say for example, the 2D Ising model. And therefore it's good at these two ends. But what it misses is that it just gets a cusp here, and there is no divergence of susceptibility in 2 dimensions. So we know from the exact solution, from variety of other information, we do know that this is what happens in 2 dimensions. There is actually divergence, but our model Hamiltonian does not get it. You could say you can do a more refined calculation to get some kind of divergence, granted, but this one at this level of approximation, if I just take it as is, it gives me this result. Okay, and I know from D equal to 3, and D equal to 3 I know from experiment, I know from Monte Carlo, I know that there is a divergence susceptibility. So it also does not help out in D equal to 3. Okay. So what is missing in these variational Hamiltonians? So what you will realize after some thought is that in this variational Hamiltonian, I have a set of uncoupled spin. No spin is talking to each other. They are like uncoupled spins. So what happens here is all the spin-spin core physics associated with spin-spin correlations, they are completely washed out. So when can we get away with something like this? You can get away with something like this either deep in the ferromagnetic state, where it's each spin is essentially behaving independently of the other spin. They are all locked in. So the fluctuations are all kind of locked away, and so those fluctuations have been reduced, and therefore those correlations are all small. Correlations and fluctuations are all small. So that works out on this end. So it is effectively as if the other spins are simply giving this uniform magnetic field. That's it. So that picture works well here. And even if you take B equal to 0 in the variational Hamiltonian, you will find that they are uncoupled spin, and that story works very well at high temperatures. So the stuff that you are missing in this regime, although you have gotten the physics of the symmetry breaking, etc., correct, you don't have the physics of correlations between spins, and this is why we are probably missing some of the quantities that we know are happening in experiments and in Monte Carlo and so on. So you could conceivably think of ways to improve on such Hamiltonians. Instead of HB, you could think of some other Hamiltonian, and I invite you to think about what you would do to improve the results. Okay, so we have come to the end of this lecture. So let me summarize what we have looked at. So we looked at the Feynman variational principle, and it offers us a route, as you have seen, to access non-perturbative regime of the coupling constant. The key idea is to get a proxy Hamiltonian with some parameters and optimize those parameters to get a good bound of the free energy. And when you apply to the D cubic lattice Ising model, we will find that there is a broken symmetry phase in any dimension. So, that is not such a good thing, particularly in low dimensions. The most encouraging part here is what I did not give quantitative information in the previous slides, but it is here now. If you look at the critical exponent that we saw for the order parameter, we will find that we found in our discussion that it is beta is equal to half. Now, you see that when you go to higher dimensions, like for example, we know beta is 0.35 or so in 3 dimensions from variety of both from experiment, Monte Carlo, etc. We know this. So, you can see that as you go higher to higher dimensions, these kind of variational principles are getting better. So, some decoupled variational principles are not good in low dimensions. So, the message is that they are getting better in higher dimensions. So, perhaps this is already telling us a lot about what is going on in these kind of systems and importance of fluctuations in low dimensions, etc. We will have a lot to discuss about this in the coming lectures. But before that, in the next lecture, we will take up another very physically motivated approximation scheme called as mean field theory, and I am sure that you will enjoy that lecture as well. So, please do join me for the next lecture. Thank you.